Okay, so we are on to dielectrics. So there is an issue with capacitors sometimes because sometimes you want to store a pretty big charge, but to store a large charge without making that voltage like super big, you would have to have a really large capacitance. Well, that is inversely proportional to the spacing. And so if you have a small space, then that can kind of cause issues too, because it can begin to break down. Like if you take two charged pieces of metal or something and you put them relatively close together, it's those electrons are going to break down the air and they're going to jump from one plate to another. So it's going to create like a spark. And so if we don't want that, then we have to come up with some kind of other sort of insulator than air, which is what a dielectric does. And so some insulating materials are called, dielectrics. And they can withstand electric fields larger than those that cause air to break down. Okay? And another advantage of placing those between the plates is that it's going to cause the capacitance to increase as well. So for a parallel plate capacitor, the capacitance is this capacitance of a parallel plate capacitor with dielectric would have this equation. Now you guys are going to get mad. I can already tell. It's this funky looking K right here, which is the Greek letter kappa, which is the symbol for the dielectric constant, not to be confused with Coulomb's constant. Okay, which is all well and good if you were looking at it, from this equation. Now just remember this permittivity constant. I hate to even write this because I just know that you guys are going to grumble at me right now. This K right here is that K. But remember that permittivity constant is like 1... oh gosh, I don't even want to do it. 1 over 4 pi K. That K is Coulomb's constant. But I would just use this one if I were you. But that is also given in the book. So if you see that, that's what that is. All right. So dielectric strength. So the dielectric constant depends on the insulating material used. So the dielectric strength is the electric field strength at which the dielectric breakdown occurs. Okay? And so, if you look over here on the next slide, you have some dielectric constants. That's this right here. And it tells you even the dielectric strength, which is the volts per meter. Okay? And it goes and shows you sort of the comparison between, air. So air is like around 1, whereas this paraffin paper or Teflon or rubber is a really good one. Paper, mica. So different things have different dielectric constants. Usually in the problem, it will give you the constant. I'm not sure on the homework. It might actually require you to look at this table. If so, I'm sure it would refer to that. So remember kind of polarization. This was in chapter 16. This is showing you atomically that those charges, when they're polarized, that they move apart. Now, whenever you're talking about something that is being insulated on an insulator, to a conductor, those electrons can move all over. They have electron flow, meaning that they can go all through the material. But on an insulator, they can just move, in their little atom. Okay, so they still move to one end or the other of their little atom space, but they don't get to go across the whole material like a conductor would. Okay, so this is showing you like the dielectric material, which a dielectric material is an insulator. But even so, you can see that the positive charges on each little atom here are over, they're facing towards the negative, and the same for the electrons. They're facing the positive charge. Okay? So, yeah, I think that was it for that one. Then we go to dielectric constant. So, this is saying, suppose that the dielectric is immersed in an external electric field. So the definition of a dielectric constant is the ratio of electric field in a vacuum, which is considered this sort of initial electric field to the electric field inside the dielectric material. So it has this equation, this initial electric field, or the vacuum per whatever electric field is inside the material. And then they have you go ahead and rearrange it to solve for the electric field inside the dielectric. So that was just this equation rearranged. All right, so we have an example. This is saying a parallel plate capacitor has plates of area 1 meter squared and spacing of 0.5 millimeters. The insulator has a dielectric constant of 4.9 and a dielectric strength of 18 kilovolts per millimeter. Okay, so first it wants to know what the capacitance is. Okay, so we've got to, I'm going to go over to this other side and write down some things that we have. So first it gave us that there was an area of 1 meter squared and a spacing or distance of 0.5 millimeters, which is 0.5 times 10 to the negative third meters. It has a dielectric of 4.9. So see, like in this particular example, it's giving you the constant. And then the dielectric strength that it's giving you is this 18 kilovolts per meter. Okay, so per millimeter, I guess I should say. Okay, we'll get to that in a minute. So first, the part A wants us to find the capacitance. Okay, so the equation that we were given for capacitance that involved area and distance was this one that looked similar to capacitance that we've had before. The only thing that it adds is this dielectric constant symbol. Okay, so I'm going to move it over here. So we have the K, which is 4.9, times the permittivity constant, times the area, which we're given as 1 meter squared, divided by the distance, which is that 0.5 times 10 to the negative third meters. If you multiply that out, let me multiply it really quickly. Yeah, you should get 8.7 times 10 to the negative 8th. Okay, and that's going to be in farads. And then they went ahead and they said, just go ahead and say 87 nanofarads, but either way works. Okay, so that's part A. Part B says, what is the maximum charge that can be stored on the capacitor? Okay, so if we go through our equations again, charge is equal to capacitance times the voltage. So were we given just straight up voltage on here? No, we were given the dielectric strength. So the dielectric strength that we were given was 18 kilovolts per millimeter. So we need to get that into voltage. Well, what is the distance that we were given? We were given 0.5 millimeters. So we can actually multiply by 0.5 millimeters here and come up with 9 kilovolts. Now do we have just voltage? Yes. So now we can take what we were given or what we found in this problem, part A, and plug it in for capacitance. So we have 8.7 times 10 to the negative 8th farads multiplied by 9 times 10 to the 3rd volts. And that gives you 7.8 times 10 to the negative 4th coulombs. Okay, and that is equal to charge. That is the maximum charge that can be stored on the capacitor. Okay, so that is the example with the dielectric stuff. I do think I have another example. I'm trying to figure out how much time I have because I feel like I've used some time. So you know what? I'm going to stop the video.